today we want to focus on the use of AI in digitalization, electrification in the building sector. Why? Because artificial intelligence, as we all know, is rapidly becoming a game changer to decarbonize the building sector, from how we plan, design, and integrate energy system to how we operate and optimize them over the time. So this is the reason why META BUILD and ZEBAI today come together to showcase not only two approaches, but two complementary approaches. So how AI can support electrification and system integration from the very early design phase, and also how AI and digital solution can improve operational performance, reliability, scalability in real buildings. So basically, our speakers today will guide us through the innovation developed in both projects and help us to understand a bit better how electrification and AI interact together to drive a more efficient buildings in Europe. We will just go quickly through the agenda. So basically, we will start with an introduction of META BUILD project by Nikos Dimitropoulos from N2A. Then we will have a presentation from Simeon Chorozoglu on AI for planning and integration, Decarbonisation-as-a-Service approach. Then we will go with Marian Angeles Gallego de Santiago from Cartif, that she will explain how to ensure reliability and minimize downtime through AI and machine learning driven solution. Then there is going to be the time to present the ZEBAI project with Antonio Latorre, the tool developed within ZEBAI thanks to the help of Lorena Cruz. And then as last presentation of ZEBAI project, we will have a demonstration, the presentation from Marjan Den Hood from GAF on buildings and scalability potential. After the presentation, we will open the floor for our panel discussion, modeling and AI for industrial sector and circular buildings. Here, basically, we will take a step beyond the two projects and look at how digitalization, AI, and the electrification come together across the value chain. So basically, from the materials and design to the energy markets to industrial operation. And our panelists will bring together perspective from industrial digitalization, Lucia Arroyo, then circular construction, and with Benjamin Constant, and the energy market integration with Dimitris Chazigiannis. So here an overview of the panelists, and now I give the floor to Nikos Dimitropoulos from N2A, who will introduce META BUILD. Yeah.
Yes, hello. Thank you, Francesca. Thank you to all the speakers and the panelists. I'll make a very brief presentation of our project. From META BUILD project. Okay, I'm skipping through quickly. Brief updates, brief introduction. The META BUILD project, called officially Powering the Metamorphosis of Buildings Toward Decarbonized and Sustainable Energy System. It's on Horizon Research Innovation Action, 48 months of duration, started in January. Now we are closing our second year. It's a very large project with 38 participants from 13 countries, and we have 13 pilot cases where we aim to electrify, decarbonize the buildings with digital solutions. 6 pilot as front runners and 7 replication multipliers, so the scope is really big. Here you can see the consortium. We have representation all throughout Europe. And we can go a bit with our vision. What we try to achieve mostly in one sentence is to power the electrification of buildings through heat pump solution mostly, along with integration of renewables and the accompanying digital solution. To do this, we optimize building energy system performance. We aim to find pathways to decarbonize the building sector by enhancing building digitalization and intelligence. So we combine hardware and software solutions to do this. Here is a very bottom-down or approach of what we're doing. Many technology enablers, many pilots. Our 6 front runners in the middle consisting France, Croatia, Austria, Greece, Italy, and Spain. We target many typologies of buildings, residential, families, single homes, non-residential, tertiary, office complexes. We also deal with retrofits and new construction. And in the second from the bottom box, you can see all of our technologies, building digital twins, just to name a few, MPC control of energy system, the heat pump solutions, which we'll see a bit later, photovoltaics, digital solutions about smart management, control, and everything between, as I said, between the hardware and the software innovation to electrify buildings. Here you can see, as we are wrapping up our second year and we are a hardware-focused project, we can say, here you can see some prototypes of what we are installing in the buildings, along with on the top left are MPC, model predictive control. So here you see three actually heat pump solutions. The R290 brine to water heat pump on the corner left, on the corner right the dual source sink heat pump, and above the R290 monoblock unit. These are just the 3 out of the 6 heat pump technologies. You also see the photovoltaics, the renewable solutions that we are utilizing, PVTs with direct lamination and air-based PVTs, and the second life batteries. So this is just a glimpse of what we are installing in the project, in the pilot buildings, the front runners and the replicators to electrify buildings. To finish up this very, very brief introduction, to understand the scope, I'll guide you through our front runners, their cases. The first one in Austria is a renovation multifamily row house in Vienna, Austria. We combine heat pumps with electric energy storage. The second one is a residential building with 130 apartments in Croatia, where we connect the heat pump solution with the existing district heating network. The third one in France, a renovation building in a historical landmark, where we install a cascade of heat pumps to electrify the gas boilers. The fourth one in Greece is about construction and renovation, where we'll deal with demand response schemes in new construction, in the new construction building and the renovated ones. The fifth one in Italy is also renovation, again, a very old building from the 1700s, if I'm not mistaken, but a lot of years ago, many years ago. Multifamily buildings where we install the heat pump solution that you saw before, the monoblock unit. And the sixth one is an extension, the tertiary building, the offices, in Spain, in Bilbao, where we extend this tertiary building with the dual source heat pump in order to provide electrification solutions through thermal and air, how the heat pump works. And here is the rest of our pilot sites, the 7 replicators, in which all of the solutions that we apply firstly in our 6 front runners, we will aim to replicate, to install again, in order to proceed with the replication, the affordability, and the potential scalability of what we are offering. Really quick, we have 7 replicators in Madrid, a hotel, university, a multi-apartment complex, Madrid, Spain, Valladolid and Segovia, a kindergarten, an educational building, Gdynia in Poland, a multi-apartment building in Riga, Latvia, a sports center, kindergarten, Mensa building, part of a university campus in Germany, in Passau, a complex of a municipality block with 4 high schools and 1 gym in Thessaloniki, Greece, a warehouse storage in Saint Priest in Lyon, France, and a single-family residential building in Plovdiv, Bulgaria. So this is a very brief introduction for META BUILD solution. Later on, you'll have the chance to hear about some of these things that we are doing within the project on the AI side of things. So this is how we combine the hardware solutions, the electrification of buildings, and we accompany it with digital solutions, with data-driven approaches to support electrification and decarbonization of buildings. Thank you very much. I think I'm just right on time.
You are, Nikos, thank you. And now I would like to give the floor to Simeon, that I would like to introduce before starting the presentation. So Simeon is a data scientist and a researcher at the National Technology University of Athens, and he will present indeed the technology that he has, that Nikos has just mentioned. And as I said, he's a researcher and a PhD candidate in digital energy system, buildings, and AI, delivering solution across the energy value chain. And yeah, basically, I can now give you the floor. So please.
Hello, good morning, everyone. I hope you can hear me well. As Francesca said, I'm Simon Horozol from National Technical University of Athens, and I will present to you a tool that we have designed in the scope of META BUILD. It is called a Decarbonisation-as-a-Service platform. In this tool, we aim to create a platform where even non-expert people regarding the energy domain can provide input about a building and its characteristics and gain insights about what actions they can apply to it in order to make it more electrified and more sustainable and lower its CO2 emissions. So first of all, a few objectives about the tool. We want to minimize CO2 emissions by applying optimized energy interventions. We want to, as a secondaries objectives, we want to improve its overall efficiency and reduce its operational costs. How we do that? We have some physics-informed model supported by AI in order to solve an MILP problem, in order to support the optimal actions in order to promote decarbonization. We have tested and validated the tool across all the pilots of the project, and we perform more experiments in buildings outside the project in order to validate it. And all this methodology we included in a user-friendly platform where the users can navigate and run their own experiments. So this is a little about the scheme of the methodology. First of all, the user logs in the platform and provides input about the characteristics of the building, like passive and active elements. The platform collects this data, analyzes it, and performs a baseline assessment of the current situation of the building and provides some visualization regarding its current status of CO2 emissions, energy performance, and operational costs. Then, from a predefined set of decarbonization actions, we call it a library or decarbonization library, we solve a mixed integer linear programming problem for the specific building, and we present the optimal solution with the primary objective of this problem to be how we can minimize the emissions, subject to some constraints like technical constraints and financial constraints, since there might be a certain amount of space where we can install photovoltaics, or the user may have a certain amount of budget to dispose for the renovation actions. So we'll continue presenting a little the interface of the tool. Here we can see the login page where the user logs in and can see its previous experiments and or run a new one. Here is also the link of the tool. It is currently running and we are constantly updating it with new features, etc. And once the user logs in, we enter the first phase of the tool, where the user should enter basic information about the building, for example, the location, some prices regarding this region, like the electricity prices, the gas prices, or the heating oil prices. We want also the location for one more reason, because we retrieve data like weather data and PV potential from external PVGIS tool. So the location is a prerequisite for this tool. And in the right side of the slide, you can see an example building in Athens where we ran the experiment. We have also filled information about the available budget and the available space for installations. Then we proceed to more detailed information about the passive and active elements of the buildings. We want to know exactly the exact status of the building envelope. For example, the walls, the doors, the ceilings, how much area do they take, what the orientation of these elements is, the shading, and some more detailed characteristics like the U value. The same applies also for the appliances, where we want information like the energy efficiency of the appliances, the weekly hours that the user uses them, information about the lighting systems, and of course heating systems, which is probably the biggest load in a building, where we want to know information like the energy efficiency of this system. In the right side is the example form where which the user should fill in, and the same form applies also for the other elements like the appliances, lighting, etc. Once we have all this information given, we through the physics-informed models, we perform the baseline assessment where we gain insights about the consumption, the emissions, and the operational costs. We break also down this information per category to show exactly how much the appliances are responsible for emissions and energy consumption, how much the lighting system, the heating system, and the cooling systems. And once we perform also the baseline analysis, we proceed to the final step of the tool, where we propose the set of decarbonization actions solving the MILP problem. We prioritize replacement actions from the library we have created, and we propose to the user what exactly should be done. For example, in this case, we should install a heat pump. With that cost, we should improve the insulation, change the air conditions, change the appliances with more efficient one, and change the windows. And after all, we assess again the building with the new values, and we have some visualization in order to compare the pre-renovation and the post-renovation status of the building, how much CO2 emissions will be saved, how much cost in savings, in financial savings we will have, how much do these actions actually cost. I want to point here that we have not included the installation cost because that may vary from country to country. It's only the costs about buying applying these renovation actions. And finally, we have also the graphs to see the comparison from the pre-renovation, post-renovation. Finally, what we are actually developing is creating a large data set from the tool with the actions of the buildings. That is because we want to enhance our AI models and integrate it to the tool. So when the user provides information and characteristics about the building, we will have more light AI models, so we have immediately actions without having to solve the MILP problem, which is very consuming in terms of resources and time, and we will eliminate it full and have instead the AI models. So this is from my side and what we have currently developed in terms of the tool. I think I am in time and I am ready to hear your questions.
If any. Otherwise, we can also go with Marian and go back to the speakers later on in case, in fact, there are some people from the audience who has questions also among speakers. Okay, So as I said now, thanks Simeon a lot to introduce the decarbonization-as-a-service approach developed within META BUILD, and also the importance of the use of AI in this matter. And now it's time to delve into the reliability and how to minimize the downtime through AI and machine learning driven solution with Marian Gallego. Marian Gallego holds a master in industrial engineering at Cardiff. She's been working as a researcher and project manager, and she has a strong and solid background in predictive maintenance. Her work includes analyzing mechanical vibration data from industrial equipment to support maintenance planning and prioritize interventions. She's also the author of several research papers and has contributed to national and international conferences and patents. So, Marian, the floor is yours. Thank you.
Thank you, Francesca. So, I will now go on to present you the progress achieved so far in our project, META BUILD, regarding the predictive maintenance tool. So, in the agenda for my presentation, I will first go through the purpose of the work we are performing. Then I will describe briefly the reliability-centered maintenance approach and the contribution to this of the failure mode effects and criticality analysis. We are using this framework. Then I will briefly go through some definitions for the reliability, availability, and maintainability indicators. The artificial intelligence approach we are following. And finally, some results so far for an application to batteries. So the purpose here for this, for the work developed here in this task is to ensure safe energy system operation for electrified buildings, so that we are able to guarantee service continuity and to reduce maintenance-related operational costs. So in the end, the final purpose is to develop a predictive maintenance tool within this framework, the reliability-centered maintenance approach, and the failure mode effects and criticality analysis. So we are setting the focus on some fault prediction algorithms for the electrified systems used in our buildings. In this case, we have some thermal photovoltaics, some heat pumps, and batteries, second life batteries. And the tool, this predictive maintenance tool, will incorporate database and machine learning prediction algorithms to estimate device states. So a few words about this approach, this reliability-centered maintenance approach. This is a structured methodology and is used often for optimizing maintenance strategies with the objective to enhance, to improve the reliability and performance of critical systems. Then we are incorporating the failure mode effects and criticality analysis to ensure a thorough understanding of failure behaviors and their prioritization. So as you can see here, there are several steps that we are following with this approach. First, we have the critical equipment selection. Here, we must include some factors to decide how critical the equipment are. These factors are normally related to the operational importance, safety implications, and also the potential economic impact of the failures. Then, in step 2, we have the definition of the boundaries. Here is when we identify which are the components or subsystems of the equipment which are most critical for the overall system's operation. Then step number 3, the functional block diagram and equipment history. Here we are including an analysis of how each subsystem contributes to the overall functionality. And here it is important also to map any interdependencies and any links that could amplify the impact of failures in specific components. So moving on to step number 4, the functional failures. Here, for each function identified, we rank the functional failures by the potential to disrupt operations, safety, or environmental compliance. Then, for the failure mode effects and criticality analysis, here is where we are assessing actually the failure modes, the severity, the occurrence likelihood, and the detection difficulty for each mode. And we are integrating a criticality analysis. For this, we are normally using a scoring system, something like a risk priority number or something similar. So we are incorporating the criticality of each failure mode. We are also considering potential consequences and likelihood of occurrence. And finally, step number 6, which is the logic tree analysis. Here we are incorporating the results of the previous step, so the criticality assessment. And we have a decision tree, so this allows us to prioritize. Normally, for highly critical failure modes, we should be assigning a predictive or preventive maintenance task. And on the other hand, for less critical modes, it's more common to use corrective or run to failure strategies. If this is cost effective always. So this would be the stages, the steps for this approach. Then a few definitions for the RAM indicators. These are contributing to the predictive maintenance performance and the reliability. This is the probability that assets perform without failure during a given operating period. Then we have the availability, which is also key. This is the percentage of time during which assets are in an operational state when they are needed. And finally, the maintainability. This is the ease and speed with which assets can be restored after a failure. These all three contribute to the predictive maintenance performance, and they are useful to optimize the inspection intervals and to reduce unplanned downtime, which is in the end the main objective in predictive maintenance. So this is the approach we are following as regards the artificial intelligence. We have first data acquisition. This means we are going to have real measurements from sensors. This will be retrieved from the pilots, actually from the equipment installed in the pilots. Then we have also some expected performance values obtained from model prediction. And we will be comparing one against the other. So by applying artificial intelligence, we will be calculating some residuals. We will be analyzing them, and we should be able to provide some detection for the anomalies. We have also some fault diagnosis methods. These are focused on the specific equipment installed, which are heat pumps, thermal photovoltaics, and batteries, second life batteries in this case. So the maintenance in this case is providing us feedback because we are able to improve our models and we are able to reduce downtime. So for the application to the batteries, which is the specific use case I am showing here, we have developed a Thevenin model. Here we have this representation of a battery by means of this electric circuit. So the inputs here for the model are data measured from the battery, mainly current, voltage during charging and discharging cycles, but also other values. Some of them are values from the manufacturer, like a capacity of the battery and other static values. And then the output for this are the estimated values for the state of charge, the ohmic resistance, the state of health, and the remaining useful life of the battery. So here you can see some results, some graphs from the fault detection models developed so far for estimating these parameters, this state of charge. In this case, we use the Coulomb counting method and the dual adaptive extended Kalman filter. Then for the estimation of the internal resistance, we perform a polynomial regression. Also for the state of health, a polynomial regression. This is linked with the internal resistance. So Here you can see for the health estimation of the batteries, these are the key analysis steps we are following. First, we are calculating residuals, as I said before, as differences between measured and predicted values. In this case, we are working with internal resistance and state of health prediction. In order to make it more reliable, we are using rolling features. So rather than actually the values of the internal resistance and the state of health, we are using values of the mean, standard deviation, slopes, and they are captured within windows every 5 to 10 cycles, are either charging or discharging cycles. So it's a more robust way to identify changes in the behavior. We are applying an isolation forest model to detect abnormal behavior, and this is based on the deviations and trends. And first, this isolation forest model will provide us an anomaly score to quantify degradation. And based on this, we are finally calculating a health index, which the value ranges from 0 to 1. So here you can see a couple of graphs. On the left, you have a representation of what would be minimal battery degradation. So what you can see represented is actually the anomaly score. So as far as we are below the threshold, we are within normal operating conditions, so out of failure. And this is the case when we have a very minimal battery degradation. Minimal because you can see a peak just at the beginning, a small one, so it would be actually very minimal degree of degradation. At the right, you can compare against a state in which we have a severe battery degradation. In this case, you can see that we are going beyond the threshold approximately after cycle number 80 something. So you can see the persistent anomalies. And before that, from cycle 40, more or less, you can see already a growing trend. So we can already see that something is not performing as expected, and in the end, it goes into a failure. So here, this is just to show you the evolution for both parameters, the internal resistance of the battery and the state of health. For the first one, on the left, you can see the measured values on blue, and the model represented with the dotted line on orange. So during the first cycles, they are quite close to each other, but after cycle number 80, there's a clear divergence. So we see clearly that a fault is occurring. Then for the state of health, we can see the same idea. In this case, we have fixed the threshold for failure in state of health percentage of 80, which is commonly accepted. So below that, normally a battery is not useful anymore. So this occurs from cycle a bit before 50, 40 something, 48. Yes, 48. It's actually the cycle number. So this way you can see how our model and our tool are able to estimate degradation and faults for, in this case, for batteries, for second life batteries. So this is it from my side. I'm happy to answer any questions when it is the time for that. Thank you.
Thank you, Maria. And I think since we are kind of respecting the agenda, maybe we can go with the other speaker, and then we can go back to you, Simeon and Nikos, for additional question. Now I would like to introduce Antonio Latorre, coordinator of the ZEBAI project. And Antonio Latorre is an associate professor at the Universidad Politécnica de Madrid, And his research focus on meta-heuristic optimization and data science. He has authored of over 25 journal articles, and is currently he has participated in 29, if I'm not mistaken, 29 research projects, leading 10 of them, and also organized numerous R&I activities, and currently chairing the IEEE task force on large-scale global optimization. And today he's here with us to give, let's say, an overview of ZEBAI, the second project who organized this webinar with META BUILD. So thank you, Antonio. The floor is yours.
Thank you, Francesca. I will try to provide a brief overview of the ZEBAI project. I will also try not to, because of my profile, I also will try not to make a lot of mistakes when I speak about how buildings in the real world are being designed and constructed, because my profile is very linked to the artificial intelligence component of the project. It is project that combines experts from both the construction sector and artificial intelligence. So basically, we have a context in which our project is born. There are some estimates. It depends on the source that you check, but that around 25% of global CO2 emissions can be attributed to the construction industry. And there is also this goal of the European Union for 2050 of reaching climate neutrality when designing buildings. And the problem is that the current progress towards this objective is very slow, and not many buildings are being designed with this objective in mind. And when they are designed, they focus mostly on one aspect, which is the energy demand of the building. So our proposal in the ZEBAI project is to try to focus on this problem, not only on this single objective, but considering multiple objectives at the same time that integrate not only demand, but also operational costs, or the circularity of the materials used during the construction, the cost effectiveness of the solution, and so on. During the project, we aim to achieve multiple objectives. The first one is the design of this holistic methodology that considers all these objectives that I have just mentioned. To apply this methodology, we rely on one particular artificial intelligence technology, which are optimization techniques based on evolutionary algorithms. We basically make buildings evolve from some random solutions that consider the input of the designers. We create variations as in nature and make them compete according to the objectives that we have defined, and make them evolve to reach better solutions with time. To conduct this optimization, we rely on simulators, as I will mention in a few moments, and also on the development of a materials and systems database. So we are curating a catalog of materials of different times that affect to all the aspects considered in the construction of the envelope of the building, and all the active systems that we are including. And finally, we will apply this methodology to 4 demonstrator cases. They are located in different regions with different climate conditions and usages and building patterns. We have one in Spain, another one in the Netherlands, a third one in the United Kingdom, and a fourth one in Ukraine. So what we want to do is include in this methodology all the knowledge that all these profiles involved in the design of CEVs can provide. We have architects, that define the geometry and select the constructed systems, engineers selecting mechanical systems, sustainability consultants and renewable energy specialists that provide their feedback according to these two objectives. And in the end, if the designer wants to do so, with all this with all the feedback provided by all these specialists, she can ask for a certification of sustainable building. The problem with this approach is that changes, suggestions made by each of these different profiles can not only affect their own areas of expertise, but other design solutions provided by the other profiles. So in our project, what we want to do is not replacing these experts, of course, because we need their expertise, but we want to try to propose solutions that encompass all these suggestions at the same time simultaneously. So we take their knowledge to provide the initial definition of the geometry of the buildings. They provide requirements, specific requirements of the designs, regulations that are applicable to these particular cases, and they also provide their input on how these objectives that we are considering should be managed. With all that information, we apply the ZEBAI methodology, we evolve those buildings, and we provide a set of solutions that can then be verified by these experts and provide make a decision towards the final results. So the idea of the ZEBAI methodology is not replacing expert knowledge, but instead assisting them to make better designs. The workflow of the methodology is basically summarizing this slide. This is the last one on my side, so I won't be much longer. We need several inputs from these experts. As I mentioned, the materials and systems catalog. We need to know about regulations of the location in which the building is going to be constructed. We need to know to get information about the environmental and location, about, for example, the weather profiles for that location. And we also need a BIM design, initial BIM design to work with. Once we have that information, we propose variations to that design that affect all these components, the design of the walls, of the roofs, the active systems, windows, glazing systems, different kind of renewable energy sources, and use a set of simulators to evaluate the building according to each of these perspectives. So this is repeated in an evolutionary loop, and in the end we come up with a set of solutions for which we are also estimating the errors, because as we are relying on simulators, we are aware that simulators introduce some kind of error. We are modeling that error, correcting that error, and in the end, with the tool that Lorena is going to present, the designers will be offered a set of solutions that they can examine, they can inspect and get insight on the decisions made by the methodology. This is basically a very brief summary of the project. Sorry for being a bit longer than expected. And now Lorena is going to present the tool we have been developing. Thank you for your attention.
Thank Antonio. And yes, before proceeding, I would like to introduce, in fact, Lorena Cruz. Lorena is a specialist in innovative tools for architecture and construction, and she's gonna present the tools developed within ZEBAI. She's managing technological projects focused on developing digital tools for architecture and construction, and her work mainly aims to turn complex processes into practical solutions, integrating energy simulation, environmental analysis, and sustainable design. And with an experience in building information modeling environments and simulation tools like Energy Plus, she will now be presenting the tool developed. So please, Lorena, the floor is yours.
Thank you, Francesca, for the presentation. well, I am going to present the ZEBAI tool. I will let you know what are the main advantages of using it. And also I will do a short presentation of the tool, so you will see a short demo. First, I'm going to summarize briefly the advantage. So here I have included some of the tools that you can find in the market and is used by the users. I have divided for the different types of analysis. As Antonio said, it's difficult to find tools that integrate all the analysis, and this is one of the goal of ZEBAI, integrate the whole vision, so you can see how good is a solution just using one tool. So we have integrated Energy Plus for the energy performance, Radiance for the daylight analysis. Also, we have integrated some material database. We have integrating how to model the cost, so the user will know the whole vision. The second advantage of the tool is to make the workflow faster and automatically. Let's explain it with an example. Here, for example, I have described the workflow of the energy performance tool. First, you have to model the building, add some information about the location, the weather data, and so on. Then you have to specify the active and passive elements of the building. For example, you have to select the materials, the type of facade, the same for the roof. You have to assign the window size, the glazing composition. You have to model the HVAC and the renewable systems and specify. And after you have specified everything, you have to run the simulation and analyze the results. But you don't do this just one time, because if you want to find a better solution, because you want to achieve a specific standard or you doesn't comply with the regulations, for example, this is an iterative task. So this is the thing that we want to do faster and automatically. Because if you want to improve the solution, you have to manually, for example, make bigger or smaller the size of the windows, or you have to manually change the composition of the facade. So what we want to do is this process automatically. So the tool will generate and evaluate multiple alternatives. And we have included different types of facade. And also we have linked this with the material database, so automatically generate solutions for all the different constructive systems. And with all these simulators and analysis that we have implemented, the tool will evaluate and will know how good or bad are the solutions. So we'll let you find the best solutions possible, given your objectives, because you will let the tool know what is more important for you within all the objectives that we have integrated. And now that you know the better what is the goal of the tool, I'm going to present you a short demo. Okay, here is the main project list where you have all your projects that you have developed in the tool. And I'm going to present first how to create a new project. So you have to name it, you have to select the building geometry. Then you have to include the location and general information. Here, as this is a very time-consuming task, we have implemented in the tool different locations that we are working on. And we have also included the information about the regulation, the weather data. So there are templates that already contain all the information, but in case you want to include a new location, it's possible. So here, for example, we are clicking on different locations, Seville, Madrid, for example, in Spain. There are different weather data. Also, we have, for example, some data that we have included about the regulatory templates here, for example. We have implemented some of them, but this is an ongoing project. And when we include new features, we are, of course, including new regulation that the tool have to comply with. The same for example, for the occupant behavior, the lighting, and other equipment templates. Then you have filled this information about the location, weather, and regulation data. We have to here specify what do you want the tool to vary. For example, you can optimize everything that is possible here. For example, the facade, the roof, the windows, HVAC, and renewable systems. Or you can specify the things that you only want to optimize. Here, we can see, for example, that you cannot optimize facade, or yes. Also, we have included here the types of the facade that we are going to implement. So the tool will try. We have included already some ventilated facade and ethics. But in case you don't want to include in your project ventilated facade, you just can unselect. And the same for the roof. Also, you can here select if you want to not have a facade very thicker. So you can select here a maximum of facade. For the windows, well, we can here select what are the glazing that you want to include or not. The same for the frame, for the shading controls, window size, and so on. Here also there is a feature because previously we have seen the categories that we have to optimize, no? But it's possible that you want to optimize the facades, but imagine that this building is going to be located in the center of a city. So maybe the main facade, you have to keep it because you have to maintain this facade. So you can go to here and from the visualizer, and you can just select this facade and unselect from the optimization. And the same for, in this case, for the windows. Then once you have specified everything that you want to optimize, you can set what are the objectives of your optimization. You can also not only select the objectives, but also you can set what is the importance of these objectives. Here, for example, we have selected 50% for the demand, 50% for the cost, but you can edit, see what is more important for this project specifically. Then we can launch the optimization, but as it takes a while, I am going to show you another project that we have already launched previously. I'm going to show you the results. This optimization was focused on the optimize the windows, the size of the windows, the glazing composition, the frame, the shading controls, and the fixed shades. And here you can see all the solutions that we found as more optimal. As you can see, there are different size for the windows, different materials, and you can check all this solution. Here there is a summarize about the heating demand, the cooling, the no comfort. Also, we can order the solution by heating, but not comfort. We can also filter the solution. So this feature will help the user to find the solution that best fit for this project. Okay. And here also you can click on any specific solution and you will have more information. You can click in any windows and see what is composed by, what are the thermal value, and everything. And this is an overview of the tool. I think that I show you the main features. Of course, this is ongoing work. We will include more interesting features. We will also optimize more complex buildings in the future. So I hope I can show you in the future more interesting things.
Okay, thank you, Lorena, for showing the tool and the video. Actually, very, very interesting. I think amongst your explanation, you have already replied to Sophie Descartes, who asked about the comfort, but in case we can get back to the topic later. Now is time to give the floor to Marjan Den Hode, Director Information Architect and Director Information and Innovation at GAIF. Marjan has studied at the University of Rotterdam and Delft University of Technology, and is one of the first experts in building information modeling within the Dutch architectural industry. And he advised clients on the strategic implementation of BIM and digital innovation. And of course, as a director, information and innovation is responsible for digital strategy, internal resource, and project planning. Please, Marjan, the floor is yours.
Thank you. Good morning to you all. First of all, I will explain a bit of our company and how we are used to work and how this process, how we are currently working, could be enhanced with an AI methodology where ZEBAI could be really helpful. So this is me and already explained. We work on several locations, prefer mostly in the Netherlands with all our portfolio, but we are already expanding our portfolio for 20 years in Belgium, and abroad, outside of the Netherlands, we are mostly involved in hospital projects. So we do this also all over the world. So our knowledge within healthcare and hospitals is interested more about abroad. I do this alone. I have a huge team. So we are currently with 90 people. We are located in Rotterdam and Brussels since 2 or 3 years already. We have an office in Brussels, and so these are all design experts, and they are really eager to have new ways of working within the projects. Our projects are they have a focus on complexity. So hospitals have a certain amount of complexity involving all kinds of aspects which need to be taken care of. And AI is really promising and really making things possible for our future as we see. But there's also some critical impacts on architecture. And so you have this curve, which a lot of you probably know, that you have this mainstream of people who are yeah, a bit skeptic maybe, but you also have this tech enthusiasts, and I assume that among us we are on the left side of the curve, and we are the innovators and the early adapters. But I want to have one slide, and then we can dream on about all the other things. But I want to have one slide where I can point out a couple of yeah, points to be aware of. Creativity is really important for our industry, at least, and it helps us to think about solutions which weren't think about before, and to combine different kind of solutions, and that gives a freedom. And what happens if an AI tool takes this over, and will people still be able to think outside of the box? Well, privacy, we are aware of. There is some job shifts. There are some colleagues within our office which are afraid of this, and yeah, we need to be aware of this as well. The environmental impact of all these machines and data centers working for us instead of the human resources. We have some data resources, and then another thing is that the lack of empathy, at least the assumption that there is a lack of empathy. And then we have some ethical and legal issues. And the funny thing is that these points, I think of them myself. I just asked ChatGPT to point out some things we need to be aware of, and this is an answer of AI, which we should take care of. This is a funny thing. For our methodology, we see AI as a part of a route. So when we have a design process, so just some small parts of the routes still can't be done with AI, but like driving a car on the highway, it could already autonomous drive certain parts of the routes, and that's how we see AI as well in our office. So when we are involved in a project, an architect is already involved early in the design stage, where people are only thinking of how many rooms they want or how many square meters they want in their project, and then we stay up until it's being built. And there are a couple of moments where ZEBAI could help us. So in the early design stage, when you are thinking about building characteristics in terms of structural choices, like do you want a concrete building frame, or do we want to have a wooden building frame? And then later on, you will think of finishes, and mostly both materials are general. And then later on, during the construction, they are being chosen to be specific. So we have different kind of levels where ZEBAI could help us identify the right choice of materials. And therefore, this database or this catalog, which Antonio and Lorena already mentioned, is really helpful. So within the design stage, we have multiple phases. So we have a schematic design and a design development and a technical design, and all these phases have their different kind of level of detail. And within this level of detail, it's really important that we don't get too detailed information at the early design phase, and don't get too rough information as well, because otherwise a tool like ZEBAI couldn't calculate the right answer for us. Our way of working is to work together with clients. So here you see one of my colleagues next to the screen working with end users. This is in a hospital, and he is designing a design proposal. And this design proposal is mostly a technical drawing, but this same technical drawing, it has different kind of being presented. So you could also see this as a 3D model, and you can also give it materialization. And with this materialization, you could also make a visualization. So this is different kind of views towards the same information. And we do this also with huge groups to give people a VR helmet on, and they can experience also the skill and also a bit of the materialization. So this is a way of how we used to work. And within the design process, we have a loop, and it's a typical design phase. It takes mostly 3 months, and you have these small loops, and the choice for the material is also a small loop within this loop. And as long as it's not the right outcome, we go back, and then up until it's more or less final enough for that stage, and then we go on to the next phase. And with ZEBAI, we dream of a tool which helps us with some kind of presets. So we have, for example, when we have a building with already some background of choices which are already made for other buildings, then you want to repeat that same preset of selection, like you want to have a nature atmosphere, or you want to have building characteristics like the U values, etc. So all these presets would really help us to do this. And then to the real life case where we are working on at the moment, it is our ZEBAI use case. We do this for the hospital in Tilburg, and Tilburg is located in the Netherlands. And you see this building here, and it's currently being built. 2 weeks ago, we celebrated the highest point, as we call this in the Netherlands. And this is a part of a huge campus. So within the Tilburg campus of the hospital, you see the existing hospital at this aerial picture. And within the dotted area, there is this building currently being built. And this is the first phase of hopefully many to come. And so this first phase is the where we focus on. And now our client is really interesting to use ZEBAI already for the preparation for the second phase. And we are currently starting the second phase for this hospital. And then we would be interested in how ZEBAI could help us with the outcome of this project. So when designing a project, you have this no material 3D model, and you want to enhance this model with materialization. Also towards a detail where it almost look realistic. And this is what our client is mostly interested in. But on the other hand, there are a lot of choices on the background, like cost and our environmental impacts, like availability within your neighborhood. And that's where this material database or catalog of ZEBAI is really helpful for. So to come back to the scalability, that was something also why this project is really promising. These two projects, this phase 1 and phase 2, it's also a part of a larger project where all these buildings are being replaced in the near future. So this is a route for between now and 2050. And so all these buildings will be designed in the next years. So therefore, ZEBAI would be really helpful for us. And we are really looking forward to be involved in such a project and use these tools with all the knowledge which all these professionals here have. So this is my presentation, and thank you for your attention.
Thank you, Martin. Actually, very, very interesting. And with, let's say, your concrete example, I see some, let's say, resemblances between the tool of META BUILD and the tool of ZEBAI in projecting the cost of materials and all the other things that we have to take into account when it comes to visualizing buildings. And we have just explored how AI-driven design and electrification can somehow, let's say, reshape the way we plan and operate buildings. But as I mentioned at the beginning of this webinar, if we really want decarbonizing the building sector as a whole in Europe, we need also integration across sectors, innovation in materials, and business models that make this solution scalable in the real world. So this is the reason why within this webinar we decided also to organize this panel that will take us beyond ZEBAI and META BUILD projects for a couple of minutes to look at how digitalization, AI and electrification converge across the entire value chain, from the materials to energy markets to industrial operations. And our speaker bring perspective from industrial digitalization, energy market integration, and circular construction. And now I would like actually to start with the industrial digitalization, Lucia. So basically to begin, we look at the sector that has already demonstrated somehow what digitalization can achieve. And we do that with Lucia Arroyo, because Lucia is an innovation manager at Electrogenium, and she worked directly with this technology in the industry sector. She has a deep experience in multi-physics simulation, machine learning, and thermal system, from automotive efficiency to industrial operations, and she now leads the development of digital twins and advanced analytics Electrogenium indeed. And so basically, let's say that her background makes her ideally positioned to explain how digitalization and real-time intelligence can actually accelerate decarbonization across sectors. So, Lucia, I would like to start with a question. How do digital twins enhance real-time decision-making in industrial environments?
Yeah, thank you, Francesca, for the introduction. And well, regarding this question, well, I can explain that we are an automation engineering company. So basically, we digitalize industrial sector. And in my department, what we are working is to try to develop digital twins to close the loop between data, operation, and optimization. Basically, we for industry, the digital twins we are using for reduce energy consumption, improve quality, and also, well, process optimization. In fact, what we had in the past, we have these controllers, the PLCs, which are the computers where we program the sensors and actuators. But now we are working in edge computing, so creating programming some hardware in order to give other characteristics. For example, introduce advanced machine learning models, include physics-based simulation in real times, and well, these digital twins can provide this additional layer of intelligence to the industrial sector. And I can see that, for example, in the building sector, I'm not an expert of this sector, but I can see some try to extrapolation. We can try to integrate these systems, this intelligence in real time to the buildings in order to, well, for example, enhance comfort, reduce energy consumption, and improve maintenance. Yeah, I think more or less I have given my answer to this question, Francesca.
Yeah, indeed. Thank you. And in fact, sorry, in this context, I'm wondering, like, what role does then edge computing? I mean, what role does edge computing play in making the systems you mentioned more autonomous and resilient?
Yeah. Regarding this question, in fact, well, edge computing is the computer that enables us to give this plus of intelligence to the actual system. So, for example, for using the edge computing, you can deploy the digital twin locally, so near the controllers in industry, because we have some restrictions normally in the industrial sector to run the digital twins in the cloud. And so the idea is to have this computer near the controller. We can run complex algorithms. We can react in milliseconds, because control of industry, well, it's about milliseconds. And well, we can connect the controller with the algorithm. And some advantages, well, you can have ultra low latency for real-time control. This is something very, very important. And also you can update models, you can include additional capabilities to actual control. But that at the end, what we are looking for is to increase resiliency and autonomy of industrial sector. And I would like to compare also with the implication for buildings. From my point of view, this edge computing, so integrate this computer near the controller, well, you can try to include or to apply predictive controls to some of the devices. You can include algorithms of maintenance prediction, and also, we can integrate this information, ensuring the data protection, not in the cloud, but also in a machine in the building.
Okay, I see. Thank you for making the comparison with the building sector indeed. Although you're an expert in industry, but that's actually very interesting insights from the industry perspective. Just because we are running out a bit of time, I will just try to go also with the other panelists, and in case we go back to questions for you and the other speaker. But now, yes, since we have started with the industrial digitalization, I would like to move to the energy market integration, because as I said before, not as I said before, but as you all confirmed, electrification accelerates and buildings are no longer passive energy consumers, and they can become actually active players, providing flexibility, supporting the grids, and benefiting from new market models through batteries, smart controls, and even virtual PV ownership. And this is actually the reason why I would like now to introduce Dimitris, who holds a PhD degrees from the Department of Electrical and Computer Engineering at the University of Thessaloniki. And Dimitris serves as an external consultant to Optimus Energy, and is a research associate at the National Technical University of Athens, focusing on energy economics, optimization theory, and mathematical modeling in energy systems. And from your perspective, how do you think, how can we better integrate buildings, active players right now, into energy markets in order to unlock these opportunities? And if I may, what policy, in your opinion, or regulatory changes are most urgent to scale models like energy sharing within buildings and communities?
Yeah, hi all. Thank you, Francesca. Actually, I completely agree with what you said at the beginning, that right now we are in the point where, large buildings or large industrial customers are not anymore passive customers, but active participants in energy systems. So, Heron is one of the largest energy utilities in Greece. So we have a large retail side clientele of almost 400,000 customers, and through a merger that is going to happen in the next months, we're going to have approximately 500,000 of customers. So, we are both a company that participates in energy trading activities by selling energy through our large power plant that we have, and buying electricity from the electricity market from our customers that we represent. But we also have our own in-house energy services, where we try to promote products that help customers to better digitalize and further increase the value and flexibility that they can extract from their own places and their own buildings. And we also participate in research programs, in Horizon funding to research programs, aiming exactly at this, to find and identify the best solution in order to give this value to customers through participating into electricity markets. And how can we do that? There is the main concept, let's say, of demand response activities, where we can aggregate various customers and participate into electricity market, harness their real-time flexibility that these customers have in order to extract value from the market and then give it back into the customers. And we also use the electricity market and various financial-based schemes in order to provide with customers with additional financial leverage. So, you know, we have developed virtual financial participation models where we emulate PVs and we give this value to the customers so they can have shares of these virtual PVs. And this enables them to practically to engage better into this energy transition. And this is something really important because, you know, these models and these financial models and are widely accepted from our and the customers, both on the residential side and also on the industrial side. Since, you know, right now, due to the high integration of renewables into Greece, especially PV power plants, there are several volatile costs. Large customers need to have some sustainability targets. We also observe a reduction in renewable capital expenses. So, you know, everything goes into this direction, and we try to use electricity markets and the capability, the technological capabilities that we have from digitalizing buildings in order to extract the value that we can from the flexible assets that currently exist or they will exist in some of the buildings and give it back to the end customers. In order to do that, there are, you know, at this point, there are several regulation, you know, drawbacks that exist. We probably needed some simpler digital permitting. We have a main issue with the DSO that we need to convince them that they should invest in solutions that will enable the active participation of buildings and end customers so that they will not have any problems with their grids. And but in general, we're working into this direction because, you know, we're at the point where as a retailer, from the retail side, you should invest in such technologies and you should invest in new financial schemes in order to diversify from your competitors and provide the best services to your end customers.
Okay, I see. Thank you for further explaining. So indeed, like about the in your opinion, sorry, like which are the regulatory policy changes that we should like in general, like not relating only to Greece, but like in Europe. I don't know if you have already said so, but like just an opinion from your side, or you can think about the answer and we just go to Benjamin, since I saw that we have not more than 10 minutes by the end of the for the end of the webinar. As you prefer, Dimitris.
You can go through Benjamin and then we can come back and other questions.
Okay.
Yeah.
Okay. And okay, thank you. Sorry, because yes, we are a bit running out of time, unfortunately. But again, we can still explore these topics even after the webinar. Now we would like, let's say, to close to wrap up with the concept of low carbon materials with Benjamin Constantin, because I would like to return to the very, let's say, foundation of our built environment. We talk about buildings, we talk about integration into the market, we talk about some parallelism with the industry, but now it would be interesting also to give a look at materials, because achieving zero-emission buildings means not only, of course, improving operation, but also reducing embodied carbon and embracing circularity. So Benjamin, he's here with us. He's a CEO of Neo Eco and leader of Neo SEM initiative, and he has over 25 years of leadership in international projects and corporate management. He is a recognized expert in circular economy solution like calcined clay. And today we are talking about that. So Benjamin, welcome to the panel. And I will just ask you like a couple of questions. First, what is NeoSem and how does calcined clay fit into your low carbon construction strategy? And also looking ahead, how scalable is this solution across the different building types and European regions in order to accelerate circularity in the building sector?
Thank you, Francesca. NeoSem starts with the firm will to have an impact on the decarbonation of construction. In fact, if you look at cement, it's about 8% of worldwide emissions. So it would be like a very, very large country, maybe the fourth most emitting country in the world if it was a country. And if you look at how pervasive is the material, you find that absolutely everywhere. We've got 40 billion tons of concrete poured every year. So we've got each of us, we've got about 5 tons of concrete per person. It's more than, it's the staggering proportions, second product most consumed after water by humankind. So it really made a lot of sense to try to decarbonize cement, knowing that it's probably obvious for a lot of you around the table, but the emissions from cement come from 2/3 from a chemical reaction, which we are going to be calcining limestone, and limestone is a byproduct of life. You've got sediments which are accumulating, and when you're going to cook it in a way, calcine it, you're going to re-emit the carbon which is stored in the material. So to do this, you need to use a lot of energy, and the energy that is going to be consumed by cement is going to be 1/3 of the problem. So 2/3 from a chemical reaction, 1/3 from the fact that it's calcined at 1,450 degrees between 1 and 2 hours. So the question is, when we talk about programs like the ZEBAI project and other projects where we talk about decarbonation, there is always almost the elephant in the room is cement or it's steel, one of the two. But these are the very emitting materials that we're going to have, and cement in Europe is a very big one. So what's the alternative? What can you do about it? The cement industry has been working on carbon capture, and it's been working on reducing consumption of energy. If you look at carbon capture and what is promised by the cement industry, it's that in 2050 there would be net zero, and this date is slipping. We're not going to be there most probably at that time. There is a much faster way and a much more economic way to do this, because carbon capture, I mean, if you know, TRL is probably 7 or 8. There is only one facility working in Norway, and it's not working to its full potential. It's going to cost billions. It's still a good solution, and we still need to do it. But frankly, there are much faster ways to achieve some decarbonation of material. So NeoSem changes the raw material which is being used in the cement. We are going to be using clay, and in particular, we're going to use recycled clays. So when you change for clay, basically when you activate the product, the material will not emit CO2. The clay is a byproduct of the degradation of minerals, and it doesn't store CO2 in itself. So when you calcine it, you will not have the CO2 emissions, which means that you're going to save 2/3 of the emissions. And then the last third, we've developed a process which is very efficient in terms of energy, and we will use about 1/3 of what would be needed in a rotary kiln for a cement industry. So that gives us a benchmark of 95 kilos of CO2 per ton, while the normal traditional CEM1 cement is recognized to be at least, the benchmark from the cement industry in France is at 823. So it's almost a 90% reduction of CO2. And you produce an SCM, so it's a cementitious, supplementary cementitious material, which means like it's a material, activated clay is a material that will come and substitute clinker in the formulation of cement. So clinker being the raw material that comes out from a kiln, from a cement factory. So it gives you an idea of what can be achieved. This plan, we started this project in quite a long time ago, in 2017, with plenty of R&D, but we've now finished constructing a plant, and the plant is producing, north from Paris, it's going to produce 100,000 tons of calcined clay. And this is a material that you can immediately use to substitute clinker and cement formulation, achieving a very it's an important gap into decarbonation that is activable right now. Of course, unfortunately, we cannot ship this product because it's quite ponderous all across Europe. For now, we plan to open more facilities producing, but the idea is that if you look at the alternatives for cement, and when you hear about calcined clay, this is a lever that will become in the future available to you and will be really contributing to the decarbonation of projects. So to your question, Francisca, does it scale? Well, it does scale really well because we have plenty of clay on the planet. Clay is one of the most important resources that you have. You have a lot of limestone, you have a lot of clay, and this will really scale well. We are using recycled clays which come from the construction industry. So say you dig a tunnel, which is our case. For example, we have, it's not us digging, it's the Société du Grand Paris. They're building 200 kilometers of underground around Paris at the moment with 68 stations. There's a lot of materials being dug up. And at the moment, we are recycling that. We have other sources, which is planned for the coming years, but really our starting point is to use that material. So we've learned how to pick the right clays and identified how to blend the different types of clays, etc. There is a little bit of construction around it, but the core idea is that not only we decarbonize, but we are also able to produce a building material without a quarry. So we are resellers of materials without having a quarry, recycling clays. And so it's quite a big deal. It's a project which is recognized by the French government as a strategic project, but also by Europe. We've won the European Innovation Fund recently, which is quite a select club, really. And we've also won the STEP seal, which is a recognition of high quality project in Europe. So that what is interesting is that when you start modeling, like what we're talking today, when you start modeling, these types of solutions need to come and be integrated as raw data, like new data that fits into the AI models that we are talking about. This is a big step. This is quite new. This is quite innovative, but this is scalable and this is available to everybody to decarbonize the construction industry. So that is a small contribution that I can bring today to say like there are new things happening and you have to stay opening eyes on what is possible. And of course, I don't want to take too much time because I'm very conscious that we're running out of time, but please feel free to contact me if you want to know more about it. This is a big deal.
Thank you, Benjamin. Yeah, it is, and you just confirmed me. Let's say the third question that I was about to ask you, which was like if you see AI and material innovation working together, and you definitely do to accelerate the transition to the circular and zero emission buildings. Thanks a lot. I don't know whether there are other panelists or in the audience someone that has question. Either way, after this webinar you will receive also the emails of the panelists, so in case you want to reach out directly to them and ask more information, feel free. And I just wanted to get back to Dimitris because I leave him like with a question, which was the one related to, let's say, the policy and regulatory changes most needed in his opinion. Because I might have lost it actually before. So Dimitris.
Yeah, sure. We can point out to some very two specific points, let's say, about regulatory changes. The one is on the technological side, and this is related actually to smart metering and to official, let's say, smart metering and all the interoperability standards that are required. And in general, the smart meter rollout, where DSOs need to install, at least I'm talking right here specifically, let's say, for Greece, because I'm pretty sure that this situation is a little bit different in other countries, in Germany, for example, but we need some official, as a retailer, we need some official smart metering data in order for us to create new business models and to provide new financial services to end customers. So we need, from a regulatory change standpoint, to enforce and quicken, let's say, speed out this smart meter rollout, because right now we have various drawbacks related to equipment cost, and also due to the fact that even if we install smart meters into our customers' houses, these are not the official measurements. So we are not very well aware of what they consume and what is the available flexibility at any point. So there is a need for a regulatory change on this part in order to speed up all this smart metering rollout. And from a market standpoint, currently there exists no specific flexibility, let's say, remuneration from residential customers. There is, from an academic standpoint, there is various research done in the field of distribution markets right now that this flexibility could potentially be procured in such markets, and how these integrate with wholesale markets where a retailer would buy energy for our end customers. And even if we do not proceed in this distribution and wholesale combination, let's say, of electricity markets, then we should see some regulatory changes related to the actual participation into wholesale markets from distributed resources, where currently we cannot do that due to various specific, let's say, obstacles that we have related to bid quantity and available capacity that we can submit into the market, and general stuff related to the whole optimization problem and market clearing procedure, where if we incorporate distributed resources also, the overall market mechanism may not be cleared in the required time that we have set for wholesale market. So, there we require some changes from a regulatory standpoint on the technological side, when we require some changes on the more financial and market architecture standpoint. And these are just, two very specific examples on this direction.
Yeah, exactly. Thank you. I actually wanted to hear, this perspective from you. And okay, so we hear from Benjamin that it's possible to scalable solution, circularity solution. We hear from Dimitris the challenges that we are currently facing when it comes to integrate let's say, smart buildings into the energy markets. Now, just to finish, I know we are a bit late, but I would like then to give the floor to Lucia, just with the last question of this webinar and panel, and to hear from her then the main challenges that we are facing in the industrial sector, specifically the main challenges that the traditional industry actually have when it comes to adopting, let's say, a smarter solution like digital twins at scale, and how can they overcome them? Thank you.
Okay, well, regarding this question, from my point of view, the first of all is the availability of data and the quality of data. There are some industries that they have a lack of some type of data, some variables they are not measuring. So, and sometimes they have all the machines that we need to communicate. So this is from my side one of the most important points at the beginning if you want to integrate a digital twin. So also the quality of data. Sometimes you have the frequency is not the one that you need for developing the digital twin. So you need to normalize, to filter some data. So this is all about data. The second aspect from my side is more about the cost and scalability. Of course, there are big companies that it is easier for them to integrate this technology, but for example, for SMEs, it's not always the case. So we try to develop low-cost digital twins in order to democratize this technology for all the industrial sector. And finally, well, from my point of view, is some about the organization and the digital skills. It's not always easy to, because for the digital twin you need to, it's a multi there are different profiles in when you need to develop and integrate a digital twin. So you need to be to take into account that once you integrate in an industry, you need to have this type of profiles in order to create well, to follow the maintenance, to update and so on. So for me, these are the main challenges, and maybe this could be extrapolated also in the forthcoming building sector integration of the digital twins.
Thank you, all of you, for being here, and see you for the next session, maybe another one about the use of AI.